All right, here's my data for one type of lab where what we did is we just shined the laser at the screen through the slits. We kept the slit screen length the same, L equals 1.4 meters, and the data sheet that the slits came with had a separation for the slits that I shot through, so I just used the data sheet to know the slit spacing here, okay? And I just went from the central bright point over 1, over 2, over 3, you just saw that, and I get these positions. I graph position X going up, order number going to the right. I get a graph that is a line, looks like a pretty good line to me, and I get a slope. That slope can help me get the wavelength of red light. Okay, so first things first, this is the equation for diffraction. What happens is when the light goes through the slit film, the light splits into little rays. Each ray has an angle from the central maximum. So the angle would be right here or right here. However, what if there are many of these? Then each of those little rays that diffract out would have a different angle, and each ray would have a different order number. That's M. The central line has an order number of 0. Then the first one to the right or left of that has an order number 1, 2, 3, 4. So however many dots you go over from the center, that's your M. Lambda is the wavelength of red light, and D is the spacing of the slits. This is not a friendly equation. However, but this is the only one on the AP exam formula chart. However, you can teach your students a nice math trick, which is this. If the X, that's the distance between the center and each bright spot, if the X is less than 20% of the L, if the X is less than 1/5, 20% of the L, then sine theta is almost the same as X over L. Now remember, X is a distance that goes up, and L is this horizontal distance, so that's really tangent right there. X over L, that is opposite over adjacent, but sine and tangent are almost the same if the angle stays small enough. If the angle's small enough, sine and tangent are almost the same. So I replace d sine theta with dx over L equals m lambda. Okay, so what am I going to do? I'm going to rearrange this. How am I going to rearrange it? X stays, m down, D down, L up. Then I say this, if X is my rise and M is my run, then this whole thing is what the slope represents. The slope is lambda L over D. I got a slope. Do you remember it? Do you remember I got a slope of 0.028? Well, here it is. I plug in my L. Do you remember it from a couple of slides ago? I plug in my L. I plug in the slit separation, I plug it in here, and when I solve for lambda, I get 6.59 10 to the negative 7, which is about 659 nanometers. Now, the laser on the laser, every laser has a federally required label. On that label, there is the wavelength. It is extremely small, and you may need a magnifying glass to see it. Lucky you bought a bunch of magnifying glasses for geometric optics, so just use one. And I believe the lasers that I use say 650 nanometers is their wavelength, so that's pretty dang good in my opinion. Of course, you will not tell your students that the wavelength is on the laser in advance of doing the lab, because it makes their faces scrunch up in this angry little face when you show it to them after they went through all this work to find the wavelength of red light. It's just precious when they get so mad. It was right on there, right in front of them. Now I made the slit screen distance different. I just moved the slits back and back and back from the board, and I measured 3 dots over from the central bright spot. I used the same slits. I measured 3 dots over from the central bright spot. So 3 dots from the center, 3 dots from the center, 3 dots from the center. Remember, I'm allowing students to choose which of these methods they want to use. And I do not give them a lot of guidance. This is an inquiry lab for me because I've already taught them about diffraction. Now they got to show me they understand it. Here's a nice line. There's a nice line right there. So I'm going to remember that slope, 0.058. All right, remember that sine and x over L are almost the same thing because that angle, that little diffraction angle, is very, 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 very small. Okay, so what am I going to say? I'm going to make x the rise and L the run. That just makes the d move down. Only the d moves. That means m times lambda over d is the slope. The slope I got before is 0.058. I set that equal to m, which is 3. That's a constant. Lambda is what I'm looking for. D is the slit screen distance. And this time I didn't do as well. I got 6.37 to the negative 7, 637 nanometers. So what? 9 nanometers off on one, 13 nanometers off on the other. If your students are careful, they'll do a good job. Variations. Give different lab groups different laser lights. Or heck, give the same group the same laser light. Have them do different laser lights and see that the wavelength is different. You can get different red, green, and blue laser bundles for about $10 on eBay. The shipping takes a very long time. It takes about a month, so order now. It's very worth it. Give the wavelength of the laser. It's all printed on the label. Give the students the wavelength and then ask them to evaluate whether the rainbow peephole actually is 13,500 slits or lines per inch. That's what it's advertised as. 13,500 lines per inch. It's not. In fact, I didn't do this, I didn't record myself doing this, but I have done it before. The rainbow peephole is advertised as being 13,500 lines per inch, which is, okay, so what do? I multiply by the number of inches in a meter, and I get this many lines in a meter. I take the reciprocal of that, and I get the distance in between slits. Okay, so what I did is actually, I did video myself doing it. I think you're going to see it here in a moment. Okay, so I just used the first order number over, and I use, this is going to be, that was the slit screen distance. Oh no, that's the distance from the central maximum over 1, and that was the distance from the rainbow peephole to the screen. And so what I said is if sine theta, can you replace sine theta with x over L? Well, yeah, if x is only 20% or less of L, which it is, I can use sine theta is x over L. I can replace that. Then, incidentally, if x is only 20% of L, then the error that you introduce with this approximation is only 2%. That's not bad. I say I can use it because x is less than 1/5 of L. So let's actually do this rainbow peephole experiment. Let me show you what it's like to get these numbers.